the end of the day. So I guess next coming up will be Justin. So Justin is currently a master's student at the U of A in computer science. He's working on artificial intelligence and program synthesis, and he's also a machine learning facilitator with Amii, as well as being on the executive team for AIMS. So without further ado, let's welcome Justin.
Awesome. Thank you, David. All right, so as David said, this will be an abbreviated version of the Machine Learning Foundations course I typically teach with Amii. Oh, wait.
Here, I got it.
Thank you.
Just stop it.
It's this way. Okay.
Perfect. Cool. Okay, so a brief land acknowledgement. So we'd like to acknowledge that the land which we're situated here is the traditional home of the Cree, the Saulteaux, the Niitsitapi, Blackfoot, and Nakota Sioux people, as well as home of the Métis. As David said, my name is Justin Stevens. I'm a machine learning facilitator with Amii, as well as currently a master's student at the University of Alberta. If you have questions at any time about this content, please feel free to email us at training@amii.ca too if you want to follow up on anything. All right, so brief overview for what we'll be talking about today. So we'll do a brief introduction to who we are at Amii and some brief introductions into the field. We'll be talking a little bit of a high-level overview of how machine learning works. We'll also be talking about the various different types of machine learning that exist. We'll be talking about the types of data that can be used as really the food and building blocks for a lot of machine learning algorithms. And finally, we'll be talking about responsible AI as well. So just to get a sense of the audience here, I want to know, how familiar are you all with the concepts of artificial intelligence and machine learning? And we'll just do a raise of hands here. So first off, how many of you would say you're an expert and know everything there is to know about the field? Anyone? All right. Okay. How about I have some experience and or education in the field? Oh, wow. Okay. So about half of the people here. How about I've done some reading and learning about it, but I still kind of want to see where else it can go. Awesome. And then how many of you, is this your first introduction to machine learning? Excellent. So we have a good split. That's great. Okay. So we'll do a brief introduction to the Alberta Machine Intelligence Institute. So at Amii, our goal is to inspire world-changing machine intelligence for good and for all. And we basically want to do this by making machine intelligence the primary driver of sustainable growth for Alberta's economy. And we want to do this through great research, talent, and businesses as well. So our objective is basically to translate scientific advancement into industry adoption. And we want to do this through a virtuous circle. So this basically means that we bring leading edge research from our Amii fellows to our partner organizations, and then we take the problems and challenges we hear from our industry partners back into the research. And this process is very much so continuous, and it results in the overall advancement in the field of artificial intelligence. So speaking of our Amii fellows are basically top researchers, and they've been part of many key advancements in the world of artificial intelligence and machine learning. So you may recognize some of the names on the list here. The majority of them are based out of the University of Alberta here in Edmonton, but some of them are also based out of Simon Fraser University and the University of British Columbia. And they've been really at the forefront of a lot of very interesting discoveries. So they've been at the forefront of artificial intelligence games research, where they had the first AI to beat professional poker players at Heads Up No Limit Hold'em, as well as one of our affiliates, Jonathan Schaefer, solved checkers in the year 2007. And they've also provided many of the foundations for other learning algorithms, such as you might have heard of DeepMind's AlphaGo. The foundations of the algorithms were developed here by some researchers, David Silver at the University of Alberta. We're also part of many other exciting developments, including competition-winning systems for legal reasoning and question answering, as well as in precision medicine, diagnosing tuberculosis in resource-limited regions. So there's a lot of really cool work that the researchers at Amii do. We help companies explore a wide range of areas in machine intelligence. The ones that are highlighted orange there are the ones that Amii specifically specializes in. So things like game theory, reinforcement learning, precision medicine there. So one of our goals is we want to help move organizations along our adoption spectrum, which consists of these 5 non-distinct stages that you see here. And we basically want to help people integrate AI and machine learning into their organization in a successful and sustainable way. So the 5 stages, they start with exploring. And at this stage, you're interested in discovering potential applications and approaches to using AI as a tool, but you're not sure how to do it yet. The second stage is initiating, which is basically they've made a commitment to developing AI as a tool and are working towards creating their first proof of concept model. Proof of concept basically means just like a limited use case that you think will be valuable for AI. The most famous example of a proof of concept was Bitcoin. It started as a proof of concept white paper, and now it's spanned into a huge industry today. So just having a proof of concept for why you want to use machine learning can be very helpful in some cases. The next phase is implementing, which is after you have this proof of concept model, you begin to integrate it into your technical infrastructure. You're beginning to see some results from the system. The next is operationalizing, which basically means that at this stage, you're now generating value for AI across multiple business units. And then finally, the last stage is advancing, which means that AI is a core part of the business now, and they actively engage in larger governance discussions as well. So as you might have guessed with the advancing stage, this is basically the really big players. Like these are companies like Google, Amazon, Facebook, or Meta. So you might be wondering, all right, if I'm interested in getting into AI, should we be aiming for stage 5 right away? And our experience here at Amii is that we do not find that the majority of companies will benefit by getting to stage 5. It's definitely not something they shouldn't try to do, but the majority of the competitive advantage that a lot of companies find are either in this 3rd or 4th stage here. So either in the implementing or operationalizing stages. So one thing you might be wondering too is how do we help companies go about progressing up that spectrum? And there's basically 4 pillars for moving up the spectrum that these will be common themes throughout my talk today. And these include data, having both a high quality and volume of data that is easily accessible. This is fundamental for the majority of machine learning projects. People, you want to have people that are very highly knowledgeable and have a lot of experience in AI and machine learning. Having an organization-wide AI strategy spanning multiple lines of business can be very helpful. And also investment in technological infrastructure and tools will be very helpful for organizations to move up this spectrum. So the take-home message for this last section is that strategic adoption of AI for companies involves explicitly identifying how they'll prioritize these 4 pillars: data, people, strategy, and technology around machine learning. So throughout, when I come to an end of a section, I'll kind of pause for questions. But if people have questions at any point, please feel free to interrupt me and ask. So are there any questions so far? All right. Seeing none. And can someone also, if there's questions by the Zoom chat, can someone just let me know, please? Awesome. So we're going to begin doing some introductions to the terminology. So what are artificial intelligence and machine learning? And as a brief notice, we'll often abbreviate these terms to AI and ML. I'll try to avoid using abbreviations as much as possible, but these are really the 2 big abbreviations you should definitely walk out of today knowing. So what is artificial intelligence or AI? And AI is basically the largest, broadest category here, and it's basically a subdiscipline of computer science. So as an academic discipline, it's actually been around since the year 1955 when John McCarthy and some of his colleagues at Dartmouth proposed a summer school to investigate some of the foundations of artificial intelligence. So it might not actually be as new as you might think. So the definition of artificial intelligence is basically the study of designing machines that replicate or mimic characteristics of human cognitive functions. So you're basically trying to mimic how humans reason about problems and go about problem solving. And this can be done through trying to mimic human reasoning or human strategizing about different things. So a lot of initial attempts at AI were very much so symbolic, trying to think about the ways that the brain worked. And now, what is machine learning? So machine learning is a part of AI, and right now it's the biggest part that's being adopted into industry, and there's a lot of research being done in it as well. And machine learning basically works by taking a set of examples and building a statistical model based on these examples. And then it uses the statistical model to make predictions about future samples. We'll break down that whole process in a little bit more detail later on, but the goal or the high-level overview is that these models basically can learn correlations of the data without being explicitly programmed to learn these correlations. So also here at Amii, we often call these models question answering machines, but we'll come back to that later too. So now the next technique is, what is deep learning? And deep learning is a technique, again, that's kind of a subset of machine learning here. And it's a very powerful technique, and it's the one that's getting the most hype and excitement right now. But it's always not the most practical technique because it requires a huge amount of data. And it typically uses a complex architecture known as a neural network, which tries to very closely emulate how neurons in the brain function. And one key characteristic of deep learning that sets it apart from machine learning, for instance, is there's often many, many layers deep in these networks. And so the approaches involve a lot more compute time. A lot of advancements in them today are due to parallelization that is offered by graphics processing units. But as many have found lately, it's kind of impossible to get GPUs. So that makes doing some deep learning stuff a little bit more difficult. So now I imagine that also a lot of you have heard about data science. So where does that fit into the picture? So data science is basically an interdisciplinary field that combines domain expertise, programming skills, math, and statistics to try to extract meaningful insights from data. So as you can see, it has some overlap with machine learning here. However, data science is much more focused on explaining the data, and machine learning is focused on predicting future data. So an example of a task that is data science, but not machine learning, for instance, is doing data visualizations. So just to kind of summarize the key terminology, artificial intelligence is enabling computers to act intelligent. Machine learning is using data, algorithms, and computation to enable machines to learn, whereas data science is making sense of data. So the take-home message from this last section here is this overlap in terminology can be quite messy, and even modern day job descriptions, like those you find on LinkedIn, they're not always sure exactly what they're asking for when they're looking for potential candidates. But ultimately, the high-level idea you should walk away with is that data plus computation can lead to some very powerful learning. Are there any questions there on the last section? All right. Hearing, oh, sorry, there's a question. Go, please. Yes, I can hear you. Yeah.
Anyways, okay. So the question is, does this mean that you said that artificial intelligence is a subcategory of computer science?
Mhm.
Would you say that that means? Okay. Thank you. Oh, there we go.
Yeah.
Would you say that that means that you would need to have some preliminary understanding of coding in order to be able to do research in artificial intelligence, or are those two not the same? You can still be active and create some kind of algorithms for artificial intelligence without necessarily knowing a lot of coding and things that have to do more, I guess, with that.
Yeah, no, that's a great question. I mean, if you want to implement anything, ultimately you will need to know coding because, I mean, artificial intelligence is written through computer programs, but artificial intelligence also involves a lot of other things. Like it involves things such as sometimes the modern day approaches involve things such as logic. And a lot of the a lot of the newer approaches these days involve statistics and linear algebra. So also, if you have a very strong math background as well, you can definitely engage in AI discussions. And even if you're not from a technical background, like there's definitely a lot of business cases that involve AI as well. So I think that everyone can be involved in the AI decisions, but it just ultimately depends on what level they want to be. Do they want to be low level, writing the code, or talking more high level? How is AI going to provide business for our value for our business?
So it's almost like if you want to implement the algorithms, then you'll have to have an understanding in the coding.
Mhm.
If you want to just advance the research, then you have to have a basic theoretical understanding of it in that sense. So okay.
Yeah, exactly. Yeah, if you want to be engaging in research, you definitely need to know a lot of math and statistics and other theory as well. But
great, thank you so much.
You're welcome. Awesome, thank you for the question. Is there any other questions in the last section? All right. So let's talk a little bit about the story of AI, because I really believe that the context to see how we got here can be really key to understanding where AI is today and where it might be going in the future as well. Because it's really a larger pattern of human history that we've gotten to the point we're at today. Let's take a time machine back for a little bit, and let's talk about the Industrial Revolution, which happened in the mid-1800s. and it changed society in many ways. And one of the major ways that it changed society was dramatically reducing the cost of manufacturing. And this reduced cost allowed for a new level of scalability that wasn't feasible before, which created many new industries and jobs. So in the picture we have on the right here, this is the Jacquard loom, which automated the production of fabric. And this spawned a fashion industry that couldn't have existed before. Interestingly, actually what you kind of see going on here is the loom used replaceable punch cards to control its sequence of operations. And this is actually considered a very important step in the history of computing hardware as well. So kind of in that vein, the computing revolution, which we've seen kind of really take off over the last few years here. This really happened in the mid to late 20th century, and it likewise significantly reduced the cost of computations. You can think back to how computers used to be. They used to be this entire room with a huge computer, and now everyone has smartphones and smart devices in front of them, and so it made it a lot more convenient and easily accessible. And this has also over time spawned many new jobs and industries as well, like the whole software development industry or computer gaming industry, or even just the internet. These are all things that couldn't have been possible without the computing revolution. So far we've seen a reduction in manufacturing and a reduction in computation. So next up is the AI revolution, which if it's going to follow these same patterns, it's a reasonable bet that it will basically reduce the cost of prediction is the really new important thing. And there's three major things that have contributed to making AI as applicable as it is for organizations today. One of them is improvement in computing power and capacity. So today's processors can be 40 to 80 times faster than the quickest versions that were available in 2013. So just 9 years ago, and we've seen that much advancement in processors. And this is kind of an example of Moore's law, where computation roughly doubles every 2 years. It's not exact, but it's kind of approximate. And we've also seen advancements offered by cloud solutions. It used to be that you have to have this huge data room or you have to do computations locally, but now cloud solutions really much so offer people the ability to, have everything on a Google Cloud service and being able to do computations on there. So the second thing is an explosion of data. So the world creates an unprecedented amount of data every single day. So each time you're going into Google and entering a search result, you're creating data that is being used to feed these huge machine learning models. So it's estimated that around 2.5 exabytes, which is 2.5 billion gigabytes of data, are created every single day. And just to put that number into perspective, that translates to each and every person creating around 1.7 megabytes of data every second. So everyone in this room, I mean, not right now, but on average, we would be creating about 1.7 megabytes of data per second. And all of this data is used to feed machine learning algorithms the raw material that are needed to produce new insights. So there's also an enormous amount of diversity in the data that's being generated and analyzed. And this can create new challenges because a lot of the data can be difficult to analyze, but it does have unprecedented opportunities for new advancements from the data and new insights that we can learn from it. And finally, there's also a lot of progress in algorithms. So the techniques that are used to basically build these machine learning models, there's been a lot of work to make them faster, to make them learn from less data, and that have increased their accuracy and speed significantly. So these three advancements have really been key for the AI revolution that we're seeing today. We have a quote from my current professor and also Amii's chief scientific officer, Dr. Rich Sutton, about AI. And he says, it's a desire to understand the world, the desire to make tools to make ourselves better, and it's really totally human, the natural continuation of what humans are. And the take-home message here is that AI is a natural continuation of human search of knowledge. And advancements today are due to three key factors: improvements in computing power and capacity with faster processors today, explosion of data that everyone's generating a lot, and then also progress in algorithms that are used to build these machine learning models. Are there any questions on this last section? All right. Hearing none, we've been talking about machine learning a lot, so let's do an interactive example to actually see how machine learning works. And as just kind of a toy example here, we're going to be talking about alumni donations. So let's say hypothetical scenario, you're the fundraising manager for your university, and you're tasked to decide which university alumni your staff should call. And obviously, you can't call every single alumni. There's far too many alumni for a given university, and you have limited staff with limited time. But your goal is to maximize the amount of donations that you're going to receive. So this is for you all to brainstorm. What factors would help you maximize donations? So when you're looking at all the people that might donate, what factors would you look at to try to make this consideration? Shane.
Are they employed?
Do they have a job? Do they have a disposable sense of income? That's probably pretty important, yeah. Yeah. Years since graduating. More older alums might be more willing to graduate because they might have more saved up. That's great. Yeah. Past donation history, that's great. That can really help predict if they're going to donate in the future or not. Awesome. So here are some factors that I said might consider that you guys actually basically got all of them here. So graduation year, income level, are they employed or not? The degree they received, if they received a master's or PhD, they might be more willing to donate than if they just got an undergrad degree. And then previous donations, so donation history as well. So let's say you have all this data actually. So then the question is, how do you decide who to call and in what order? And to kind of make this more concrete, I don't know how well people in the back might be able to see this, but we have 9 alumni that we have up here. And can everyone read that actually? Okay. So in the back, okay. Who might you consider calling from this list here of 9 people? Who would you ask to go for it? Okay, so we look at the previously donated and we see Jaden, Mehdi, Emma, they've all donated before, so maybe call one of them. That's great. Anyone else? Who would you call first? You got to call one person on this list. Who would you call to ask if they would donate? Rafa.
Maybe Emma, because I see a bigger number there.
Yeah. Emma is making a 6-figure salary, graduated 2008, has donated before, probably pretty likely to donate again if they're making some good money. Awesome. Some maybe also even a Leo. I've heard from people in the past that actually people who make that $50,000 to $70,000 range are sometimes more likely to donate than people who make 6 figures. I don't know why, but apparently that's a thing. And they also graduated a lot longer ago. So there's a lot of different ways that you can go with this. And as you can see, we only have like 9 data points and 4 categories as well. And it's already beginning to be a little bit hard as we're trying to logic in our brains, how would we weight all these factors and who would we ask to donate? So one way we could go about doing this is we could try to use logical statements. So we could do things such as, if they graduated in the last 5 years and their annual income is above $60,000 and they hold a degree from the Faculty of Engineering or a social science degree, then we think they're highly likely to donate, so we call them first. But realistically, as a human, how many of these factors do you think you can consider if you write a logical statement for each? Like, let's say you're tasked with this. How many would you want to consider before you say, this is just too much for me to do? Yeah.
Maybe like 3.
Yeah, 3, maybe 4. I mean, if you think about each logical decision kind of making it a branch in a tree, each time you have a new decision, it doubles the number of branches you have. And over time, you can see this really quickly is going to explode into a very complex problem for people to solve. And then you would also have to think of how much time would it take you to parse through all this data? We just had 9 people up on the last slide, but let's say you have 10,000 people you're going to parse through. That would take an 8-hour workday just to maybe decide on a few people who to call. And then also, how would you weight all of these factors here? Because obviously some factors might be more important than others. So we can really quickly see that even in this toy example, this turns into a very complex problem very quickly. And this is where machine learning comes in. So machine learning algorithms basically analyze examples of your data to build mathematical models. And so in this case, it might analyze past examples where it says, okay, these were the person's features, like these were the year they graduated, the degree they received, and this was whether they donated or not. And based upon all these past examples, they'll build these mathematical models to try to predict future data. And these models exploit connections between each factor and the desired output, which would be whether they donated or not. And the great thing with computers is they're really good at doing math and the busy work that humans sometimes don't like doing. So machines can weight many, many more factors than humans can, and potentially even uncover new insights in doing this as well. So basically, to use machine learning for this alumni donations example, you would take all the factors that you have available that you think may be important, and then you'd let the machine learning algorithm actually calculate how important each of these factors are based upon the examples. And as a note here, the more examples of past donors and non-donors as well you have, the more accurate your system will be in general. And one thing that's really cool about using machine learning for some problems is it can uncover new insights that you wouldn't expect. So for example, Discover, which is a leading US consumer lender, they turned to an AI company in 2018 to help build an AI-based credit solution to determine how likely people were to give back loans. And it discovered a lot of very interesting things. It discovered, for instance, that if a person had a history of discount store shopping, that boosted the application's chance of getting a personal loan because maybe they thought more about their finances. Kind of surprisingly, and I wouldn't expect this, writing the full legal name of an employer on a loan application actually lowered their chances. I still don't fully understand why, but apparently the machine learning algorithm uncovered this. And they also found that if a person had called from a landline or a cell phone, rather than using Skype or an internet-based phone service, that increased their chances as well, because then they were easier to trace back rather than kind of being more anonymous. So by using machine learning, it can either help confirm our intuition about something that we already suspected before, like maybe in that alumni example, we expected that if someone's donated in the past, they're likely to donate again. But our intuition may not always be right. Like in the alumni example again, maybe people in the 50 to 70,000 income range are more likely to donate than someone in a six-figure range. So machine learning can really help to remove the aspect of human judgments that needs to be applied to some of these problems. So the take-home message here is that the power of machine learning lies in the machine's ability to build a model based on examples. So human expertise is needed here to select the important factors. However, machines need to decide how important each factor is. So basically, you decide what, and the machine decides how much. So I'll pause here. Are there any questions on this last section? All right. Hearing none, let's talk about the machine learning process in general and how it works. So let's say you have an important example that you really need an answer about. So maybe it's an incoming email to your inbox and you need to determine whether or not it's spam. Or maybe you need to know how likely it is that a piece of equipment will fail in the next week. So whatever domain you're in, this example is important to you and it's important right now. So this important example goes into the machine learning system and you get a helpful answer out. So maybe the machine tells you that no, in the first case, this email doesn't look like spam. Or maybe in the second case, there's a 73% chance that your equipment will break down in the next week. So this process kind of looks like magic, right? You get something important in, you get a helpful answer out. It's magic, right? And of course, it's not actually magic. It's what we here at Amii like to call a question answering machine, or a QAM for short, so QUAM. Well, I typically just call it a question answering machine. It's not a standard term yet, so don't try Googling this term, but we like this term over calling it a model because the word model is used in almost every industry and discipline, and it means different things to different peoples. So basically we use the term question answering machine to avoid that confusion that sometimes the word model would create. So over here, I've just kind of flipped this example here. We have new data going into the question answering machine, producing a helpful answer. But how does this actually learn? How do we actually get this question answering machine that is able to uncover these insights? And to build the question answering machine, you have to basically start with a big pile of learning data. And how much learning data you need will really vary a lot depending on how complex a problem you're trying to answer and how complex the technique you're using is as well. So even in fairly simple problems, you do generally need a lot of data. And in general, the more data you have, the better. But this is kind of, again, the garbage in, garbage out thing that we heard about a little bit yesterday, where if the data isn't of high quality, then it might not be that good. So in general, you want a lot of high quality data. So you also want the learning data to be as similar as possible to the new data that is going to be fed into this question answering machine. So let's say that we have an example here. You want to recognize whether a photo contains a cat or not. So you want your data set to consist of all different types of photos of cats. So I'm a cat owner myself. I have a lot of cats. So when I think about this problem, I think you want to have all different shapes and sizes of cats. You want to have all different fur patterns, all different lengths of fur that they might have, all the different poses that the cats might be in, all the perspectives of a picture that this might be taken. So as an example of where this can go wrong, I have some pictures of my cats here. So if I just train the machine learning algorithm on my cat Pumpkin, which is shown right there, it's the orange short hair cat. If I just train the machine learning model on Pumpkin, it might be more difficult to recognize the photo on the top there. And it's kind of difficult to tell, but there's actually 3 cats in that photo there. We have a big Maine Coon and then 2 other cats in that photo as well. So if you might not have even thought about that, you might just have trained on single photos of cats, and then your machine learning algorithm is trying to detect a photo of 3 cats all together, and it might struggle. So you really want to make sure your data set is as diverse as possible by capturing all these different scenarios that might exist to build a powerful question answering machine. And the learning data should also contain examples of counter examples rather. So if you just train it on pictures of cats, that's great. I have many, many photos of my cats, but if I just train it on positive examples, then the question answering machine would probably learn to predict that everything is a cat, which of course is not true. So you also want examples of things which are not cats to be to train your question answering machine as well. So once you have all this learning data, which is hopefully very diverse and covers a wide range of scenarios, you would then run it through a learning algorithm to produce a question answering machine. And just as a note on terminology here, a lot of people will refer to the algorithm as something that's giving an answer. However, that's not actually correct. An algorithm is basically the thing that takes the learning data and uses it to produce the question answering machine. So you can almost think of it like a blueprint. Like if you consider a blueprint to build a plane, for instance, the blueprint itself doesn't actually fly people across the air and get people to their destination. It just kind of gives the steps that you would use to create the airplane in that case. And in the very same sense, the learning algorithm here isn't producing an answer, it's producing the question answering machine. So this is basically, this whole process I've talked about here is the question answering machine development phase, which learning data goes into a learning algorithm, produces a question answering machine. And then we have this second phase here, which is the testing and production phase, which at this point we take new data, which was sometimes called operational data, and then we put it into the question answering machine to see what helpful answers it gives us out. So everything which I've just talked about here, this whole picture, we often refer to as the science side of machine learning. And this is only one half of the picture. There's really 2 parts of this picture here. And the other half is the business side of machine learning, where you have a desired outcome. You want to see what action needs to be produced to get that desired outcome, and then what judgments will apply to that action, and then also the whole context here. So there's kind of 2 sides of this coin, and I won't focus as much on the business side of machine learning today, but just know that it's a very important part when companies are thinking of adopting machine learning as well. So these 2 sides of the coin, the science side and business side, is basically the entire machine learning process. And this is what organizations should strive for when they want to see real value from using machine learning. So the take-home message here is that the machine learning process consists of taking existing data and a learning algorithm to build a question answering machine. And then this new data can be fed into the question answering machine to get new answers. Are there any questions on this last section? All right. Hearing none, I've been saying the word question answering machine a lot. Let's break that down a little bit. What makes actually a good machine learning question? And in general, when we consider how machine learning works, It looks at hundreds or thousands of examples, and it uses these examples to build a question answering machine. So we want a good ML question to be both about a single data point. It needs to be both specific and well-defined. And we also wanted to ask for a prediction about a future data point rather than necessarily an explanation. So here's a question for you all. Is this a good machine learning question? Can we use machine learning to distinguish which patients have metastatic cancer from biopsy slides? What do you all think? Give me thumbs up, thumbs down. Good question, bad question. See, thumbs up, thumbs down, so-so. I would argue that this is not a good machine learning question. And the reason why I'd say it's not is the first part of this, can we use machine learning? This isn't actually something that we would put into a question answering machine. This is a research question. So this could be a topic for a thesis topic or for a research publication, and it'll be great for that. But if we want to use it to build a question answering machine, it's not going to be helpful for us. And the other thing here is notice the plural here, biopsy slides. The plural means it's not about a single data point. When we're trying to come up with a question that we're going to ask a machine learning model, it's much easier to ask it a question about a single data point rather than about hundreds or thousands of data points at a time. So let's say we still have a bunch of data about biopsy slides, and we want to see, can we predict cancer based on these biopsy slides? What do you all think might be a better question that we might be able to use here? And as a reminder, we want it to be specific and about a single data point. Yes?
What demographic would be more susceptible?
That would be great. We could definitely answer. So what demographic? So we have all this data about the people. What demographic would be more like susceptible? So yeah, we could definitely answer that with machine learning. But again, that's not going to be about a single data point though, too. So that would be a great research question. But if we put that into a question answer machine, we might not be able to get the answer out that we wanted. Yeah, Maya, go.
So I would say that we'd have to narrow it down instead of it being a bunch of slides that we're trying to find data for, narrow it down to just one specific thing that we're looking for. So I guess literally just make it from looking for information to just one specific thing based on what we've learned.
I think that's great. Yeah. So maybe we could ask something like, does this one particular slide show evidence of cancer cells? And this is something that could be easily, not easily done, but this is something that could be answered by a question answering machine now, because it's specific about a single data point and it's very clear. All the other questions are great research questions, which can lead to some very interesting publications, but they're more difficult to work in the context of question answering machine. So I guess to highlight it here, this is a better question because it's both about a single data point, it's specific and well-defined, and it's also asking for a prediction. It's a lot easier for machine learning systems to make predictions in general than explanations. We'll talk a little bit about explainable AI a little bit later, and we'll see that it's a very difficult problem in general. So the take-home message here is that the question your question answering machine will answer needs to be the right one for the business application that you're using it in, and it needs to be about a single example using specific, well-defined terms, and it also should ask for a prediction instead of an explanation. All right, so are there any questions about this last section? Yeah, Rafa. Oh, Maya, yeah.
Can you give us an example of something that would be asking for a prediction and not an explanation?
So just the last thing that we had here. So, oops, where is it? Does the slide show evidence of cancer cells? That's a prediction. You're trying to predict.
It would be like a yes or no based question instead of something that requires. Okay.
Exactly. So it'd be something that, and we'll see in the next section the different types of questions that can be answered using machine learning. But in general, it'll be maybe something that's a yes or no, or it might be a classification task, or certain things that we're about to discuss. Yeah.
Can I ask a question from a previous section?
Yes, please. Yeah.
I'm gonna go this one.
Sure.
I'm familiar with how supervised learning or reinforcement learning, you can basically have your model identifying the wrong thing. But in the example where you talked about, and now I'm forgetting. Oh, right. It was when if people put out their employer's full name. So in that case, like I'm just curious, like, or in cases like that, what factors might make it such that it's not that basically it's extracting the wrong pattern, if that makes sense. Like, is there any possibility where I'm not necessarily saying that was an incorrect extraction, but I'm curious, like, in what cases might there be an incorrect extraction like that?
I mean, ultimately, it'll come down to, I mean, machine learning algorithms are susceptible to learning spurious correlations, like correlations that might not actually exist. And in those cases, it's very susceptible to potentially picking up on a variable that doesn't actually impact the answer as much. And it can be if the data wasn't collected in a good, consistent way. Maybe there's some discrepancies or some fuzzy areas. So it's very possible for this to happen. And we'll talk a little bit later on too about how bias can creep into these models too, and not just maybe pick up on something that's not a good factor, but actually discriminate against groups of people, which should obviously be terrible for machine learning algorithms to do. And sorry, go.
Oh, right. So then as a follow-up, like what's like a robust approach to making sure that in unsupervised learning, the patterns that you've extracted are actually truths and not just like obscure correlations? Or does that just then become a question of explaining what it's found?
Yeah, it's a little bit of a matter of being able to explain to someone else how the machine learning system got to this point. So a lot of instances of machine learning that are being used for people applications nowadays, like for hiring, for instance, they have to be transparent. So they have to say, you know, we chose to hire or we chose not to hire this person based on XYZ criterion. So the more transparency that the machine learning model can provide, and there's been some work done in explainable AI recently to be able to say, you know what, in this sentence, like for example, like maybe you have a movie review, which consists of a bunch of words. And the machine learning model could say, you know, we looked at these specific words to predict whether or not the movie review was a positive review or negative review. So being able to pick up on that can be really helpful.
Okay, thank you. Yeah.
Welcome. Awesome. Any other? Oh yeah, go please.
This is actually just related to the previous slide. Yeah. So was there a reason why, you'd say the last point, calling from a landline or cell phone would basically change someone's chances at getting something? Like what would be the difference? What is it that's really being observed here?
Oh, so sorry. Yeah, to complete that sentence there. So to increase their chances of getting a loan, or specifically repaying back.
What would you say that would be a reason why the algorithm would be looking for data?
I mean, it just depends. I mean, it would look at maybe the phone number that someone called in when looking for a loan application. And then the data set would have the true label too, like whether or not someone paid back the loan or whether or not they defaulted on the loan. So if it found that a lot of people who defaulted on loans are calling from internet services, whereas a lot of people who paid back the loans were calling from their actual cell phones, they might pick up on that correlation then. Does that make sense? Awesome. Cool. Any other questions on what we've covered so far? If not, I think now's actually a great break time. I think we're basically right at coffee break. So we'll have a 15-minute coffee break and we'll come back here at 11 o'clock to do the second part. So thank you.